Good afternoon. On behalf of Engineers Australia, I'm delighted to welcome you all to our Infrastructure Thought Leaders series, Non-Combustible Facades. My name is Amanda Rogers and I will be your host for tonight. Firstly, Engineers Australia acknowledges the traditional owners of the land and recognises their continuing connection to land, waters and community. We pay our respects to their cultures and to elders, past, present and emerging. Before we get started, I'd like to acknowledge that this evening's webinar is being hosted with our industry partner, Brickworks. Brickworks Building Products is one of the world's largest and most diverse building material manufacturers. The company has built an enduring reputation with their customers for their innovation, professionalism, and dependable products and services. As Brickworks Building Products expands globally, they continually foster and advance their products and brand, continuing to lead the way through design, style, innovation, sustainability, and collaboration. With a broad portfolio, manufacturing and sales facilities across Australia and North America, Brickworks is uniquely placed to service the demands of the building industry. Please enjoy this short video from Brickworks.
Throughout the past 110 years, the face of building materials has continued to evolve. We're here for a lifetime of living. This is Brickworks. More than brick, and more than just building products, we are a foundation for today's lifestyle and a leader for today's style. We manufacture a wide range of building products like no other. Local and international innovation, sourced from around the world to exceed customer expectations. Distinctive and luxurious products, beautiful products that stand the test of time. Building inspiration and innovation with an unmatched standing of style. This is Brickworks.
I'd now like to welcome our first speaker for today, Blair Stratton. Blair is a founding partner and manager of major projects for Red Fire Engineers. He has over 14 years' experience as a fire safety engineer in Australia and New Zealand, and has led the fire engineering design for significant infrastructure and building projects, including the Victorian Desalination Plant and the Tasmanian Museum and Art Gallery redevelopment. Blair has spent much of the past 5 years reviewing issues relating to combustible facades and has developed risk assessment techniques that have assisted owners, builders and regulators to understand and manage facade fire risks. Blair held the position of Chair of Engineers Australia's Victorian College of Leadership and Management and is currently Co-Chair of the Victorian Society of Fire Safety. Blair recently became a Fellow of Engineers Australia. Please join me in welcoming Blair Stratton.
Hi, thanks Amanda. I'm Blair Stratton. I'm the Manager of Major Projects for Red Fire Engineers. That really means that I do difficult things that come to our office, historic buildings, bridges, tunnels, rail level crossing removal things, and as of late, a lot of cladding. So for the last 5 or 6 years, I've spent a lot of time dealing with the problem of fixing combustible facades, and that's what I'm here to talk about today. So the obligatory history lesson, I'm sure a lot of you have gone to cladding presentations and you've heard all about the fire of Rome in AD 65 when Nero fiddled and Rome burned. And that was actually an example where fire was spreading from building to building throughout the city. The following year, effectively a building code was enacted and required facades to be built out of brick or stone, concrete not having been invented at that point. So the intention there was to avoid burning our cities down. And this is really an example of a reactive building code solution. And of course, as time progressed, we forget these lessons from antiquity, and we have the fire of London, we have the fire of Chicago, and we have other sort of citywide fires. And in fact, these citywide fires still happen today, although they don't necessarily make the news so much. We have fires in slums in Sao Paulo and parts of India, and these devastate communities. They take a long time to put out. They release a lot of pollution. They occasionally kill people, although fortunately a lot of them are slower moving than the topic of today's presentation, which is actually high-rise facade fires. But the lessons from history, we seem to keep forgetting. We come up with new materials, and we have the desire to build bigger, better buildings, and we clad them with plastic materials because they look good and they insulate our buildings and keep us warm. They keep the weather out. And then, unfortunately, we have a carelessly discarded cigarette butt, or we have a welding fire, or we have some fireworks, and unfortunately, we lose property, and tragically, we occasionally lose lives. And in the case of Grenfell and some of the fires in China, we have lost quite a few lives in a single incident. And these are unacceptable, catastrophic failures of building codes and building regulations. So probably the most comprehensive source, as most people are probably aware, is Wikipedia for almost everything these days. There is a very decent listing there compiled by experts such as Guillermo Rain and his colleagues. And as you can see from the first half a dozen or a dozen on this list, these aren't actually third world countries where we're having these facade fires. In fact, none of the first 9 on this page are what we would consider second or third world countries: UK, Germany, Japan, USA, Scotland, Canada, and add to that in later years Australia, the Middle East. So why is this happening? And of course, we can see the trend is increasing. Now, maybe because news sources are biased towards larger fires, and there's more sharing of videos and news media, that sort of thing. Despite internet censors around the world, a lot of this information gets out very quickly, and that seems to be accelerating. So it may not be necessarily an exponential correlation as we see, but it is a concerning trend. And certainly in that 2010 to 2019 era was when building practitioners and regulators around the world really started to take notice that this is an emerging trend and something's gone quite badly wrong. So we've established it's not a third world problem, and of course we all watched on in horror, and we're still following the podcast and reading the reports that come out of the Grenfell Tower inquiry, where the tragic loss of human life occurred. So these are generally, they're external fires by definition. They're cladding or facade fires. They can originate really in 3 different ways, as Nathan White from CSIRO pointed out in a paper actually before the Lacrosse fire. You can either have an internal fire, say in an apartment. In this case, at Grenfell, it seems to be a refrigerator motor spark ignited something. You could have a fire that emerges from within a cavity, or you can have an external fire such as arson, or a fire in an adjacent building, or an exploding petrol tanker that ignites the edge of the building. Now, ordinarily, the building code says external walls should be non-combustible, and therefore a fire like Grenfell should not happen in any of those 3 scenarios. You either have an apartment fire that's contained within a fire compartment, or you have a cavity fire between the internal and outer skins of an external wall, and that doesn't really go anywhere because you've got nice solid cavity barriers and limited fuel load in those areas for a fire to actually move, or because an external fire doesn't ignite the cladding because it's non-combustible. So clearly something has gone wrong for a Grenfell Tower fire or something of that proportion to happen. And so I've touched on some of these issues. Why does this keep happening? And I think there are all of these and probably a lot more reasons, but I'll pick out a few from this list. But the one that really, I think, started this all off in terms of the modern high-rise plastic skyscraper problem is creep. these aluminium composite panels, they started off as signage materials. They look good for advertising your dry cleaning service or your industrial storage warehouse. They were easy to screen print, lightweight, easy to erect with minimal structure. And then architects and others decided, well, actually quite like the look of that. Can I just get it in plain silver or black or whatever colour I want? And instead of a sign, it's now an entire side of the building in some cases. In the case of Grenfell, the building was recycled, or in fact upcycled. The cladding project was a relatively recent addition to a 1960s or 70s building, where they intended to make the building look prettier and at the same time introduce some energy efficiency to the facade. But in doing so, they chose materials that potentially by themselves, but certainly in combination, obviously resulted in a tragic outcome of what should have been a rather benign apartment fire turned into a full building exposure. We are moving buildings closer together. I think anyone who's looked at the property market anywhere in Australia realised that a quarter-acre section with a single dwelling is going to be rare and rarer going forward. But when we build these sort of infill developments out of combustible materials with aluminium composites, or especially the sort of 3 to 4 stories, we're seeing a lot of expanded polystyrene. And again, that should never be used as an external wall material for a 2 or 3 story building, but it's happening all the time. And these are failures of practitioners to understand the building codes. They're failures of regulators to regulate the building code properly. I think all of the inquiries that have happened after Lacrosse, after the the Grenfell fire, the Shergold Ware report, the Hackett report from the UK, these have all indicated the 4 errors at the end of the slide. So my intention today is not to go into detail into what happened at Grenfell or why the fire spread in a certain way or how you would analyse it, except to say that this is a complex problem from at least 3 very high subsystems. So the fire behaviour itself was highly complex because of the materials, geometry, etc., everything I've listed there. The egress system for that building, it was a single means of escape high-rise building. Now, that happens occasionally in Australia and New Zealand, but these are actually very difficult buildings. Even if you don't have a cladding facade fire problem, they're very difficult buildings to evacuate properly. Now, a single stair for a high-rise building in London complied at the time it was built in the mid 20th century, but is not necessarily what we would do today. So then compounding that problem by adding combustible cladding, that meant that a simultaneous full evacuation may not have worked, is adding layers of complexity on the problem. Now, it happens that across most of the UK for high-rise towers is actually a defend-in-place strategy is employed at most high-rise buildings. That means if you find out there's a fire in your building, unless you're on the fire floor or directly affected, you're told to wait in your apartment. Because if you go into the stair, especially if there's only one stair, you might block the people who really need to get out of the building. You might block the fire brigade who really need to get into the building. Your presence in the stair could be an obstruction to someone who really needs to use the stair. So the defend-in-place advice was enacted in Grenfell, and even very late in the fire, the 999 operators were giving the instructions, because that was what they were trained to do, to residents who were calling from the upper floors saying, "What should I do?" And they were told, "Stay there, someone is coming to get you." Ultimately and tragically, that obviously did not happen. The firefighting response, for the opposite reasons, was very difficult. Getting firefighters into any part of a single means of escape high-rise building is a momentous exercise. It's massive in its complexity. I think at its peak there were something like 100 firefighting response vehicles at Grenfell, and yet we still had the tragic loss of life. There is no magic water bombing cannon that can come in and douse a fire of this magnitude. Even the best reach of the best fire brigades in the world can only get to about 60 or 70 metres above ground. And that's assuming they can actually get close enough to the building and yet far enough away to deploy outriggers and still reach the building with a hose string. These are complex problems and best avoided at the source by dealing with the materials. In the hierarchy of engineering controls, eliminating the hazard is always the most effective risk control, because if you've eliminated the hazard, you've eliminated the risk. If you retain the materials or use a less combustible material, you still have a residual risk that ignition can occur, that fire spread may occur, that people may be affected by that. So all of these complex responses to a fire really shouldn't have even have to be enacted, because the building shouldn't have been built this way. Now, in terms of my job as a fire safety engineer, people often assume that we can run a model and predict how things are going to behave. Now, that's true to a certain extent. We have pretty good tools to predict where smoke is going to move in a large open compartment. Predicting external fire spread with multiple materials, though, is not just cutting edge or bleeding edge fire science. It's beyond the realm of possibility. We have so many variables, and in fact, I've listed 8 of the materials that were found just in a wall section of Grenfell Tower. The most complex fire models that we have struggle to run 2 different combustion reactions. And here we've got 8 or 9 different combustible materials, some cellulosic, some plastic, some that melt, some that stay rigid. We've got a whole range of different responses of individual materials. So to assume there's some magic way of rolling these up in a ball, throwing them into a fire model and predicting the outcome is not possible. So when we use combustible materials as part of a facade, the only real tool in our toolbox is testing, but that's expensive. So in terms of materials, and I won't dwell on this in huge detail, but just to pick one material, polyethylene, that's a material that melts and it drips and it forms droplets that could be flaming, that could extinguish on the way down, or as the fire really gets going, you could have basically rivulets of plastic molten flame that's running down the building. So while we've got fire flames spreading up the side of the building, we also have debris raining down on the balconies and on the combustible panels below where the fire started. So talk about a complex fire brigade response. How do you deal with a fire? You don't even know where the base of the fire is. It started on level 15, but by the time you actually turn out to site, you're getting sprinkler alarms going off in level 12. What's going on? And it's because of these complex behaviours with these combustible materials in unusual orientations. Now, I wanted to just illustrate using a really simple point, and I've taken this from Luke Bisbee's testimony to the initial part of the Grenfell inquiry. The same material, it's a material we're all familiar with in 3 different orientations. And clearly, we've got very different flame spread rates. We've got a change in material properties on the right. We've got self-extinguishment in the middle, and we've got a slow horizontal burn on the left. So from one material, if I didn't know about the orientation, I couldn't even begin to predict how that material was going to behave. If you've got 2 materials, a book of matches, for instance, predicting how fire is going to spread from one to other is actually a complex problem. Predicting how that's going to happen in a large or a full-scale fire is very, very difficult. So manufacturers, they want to sell products. They want to sell their best products, the Rolls-Royce cladding. They want to get on every project. They want to have the best insulation because they care about climate change. They care about green credentials. Owners want these things too. They want their building to be prestigious. They want it to be warm and comfortable. And so we rely on fire testing to allow certain combustible materials that have failed the initial screening test for combustibility. So not all combustible materials are bad. Some are very bad, obviously, and in combination, moderately bad materials become very bad, depending on the orientation and their combination with other materials. But in the building code realm, this is the case around the world, we have classification tests that are generally small-scale fire tests. So you might have a cone-shaped heater with a constant heat flux from a heating element. You might have a spark igniter and a 100 millimeter by 100 millimeter sample of the combustible material. And you turn that heater on and you see what happens after 40 seconds or 10 minutes or whatever the criteria is. You run a mathematical correlation and you'll say it's group alpha or group beta or group gamma. And gamma might be unacceptable and alpha might be acceptable under the building code. That doesn't really mean much, because that 100 millimeter by 100 millimeter sample that you threw into your cone calorimeter doesn't actually tell us what happens if you flip it on its side or if you have a 1 meter by 1 meter section of your combustible material. So these material tests, they classify and rank materials under certain conditions, but they can be very limited use, especially when looking at a complex scenario like a facade fire. This small-scale test can actually be misleading. A material that gets a spread of flame index of 0 under the Australian standard 1530 part 3 sounds like a very good material until you realise that the worst types of aluminium composite panels with 100% polyethylene core routinely got spread of flame indexes of 0, the very best score on a scale of 0 to 10, and yet the worst performing materials in facade performance. Expanded polystyrene is also quite notorious for this sort of behaviour. It gets reasonably good small-scale test results because it shrinks away from its heat source and doesn't tend to ignite under a limited ignition source. But if you put that in a rigid location, or if you put it into a vertical location, or if you put it above a balcony where the melted polystyrene is going to pull on the floor of the balcony and it can't escape the heat source, then eventually that polystyrene is actually going to flare up and spread quite spectacularly. And polystyrene has one of the best heat densities of any material that we use in the building industry. Polyethylene is another order of magnitude almost again, but polystyrene is a really bad material and yet gets quite good small-scale test results. So what we're left with is facade scale tests. And I believe Cathy has an example of some facade scale testing. So I've not got a video, but wait for that later in the next presentation. But even these facade scale tests, they're not full scale tests though. They are limited to a 3-story scenario. And the outcome of these tests still requires a qualified fire engineer to evaluate them. We shouldn't just be looking at a classification, whether it gets an EW performance classification under AS 5113 or whether it fails that test. We should actually be asking for and looking at the full test results, the reports. I guess just a final note on full-scale testing. They are expensive, but unfortunately you can't predict what a minor change to your wall system, what the impact of that is going to be on an untested system. So if you test it with bracket system A and you want to sell it with bracket system B, unfortunately, really what you have to do is go and test the exact same wall with your new bracket system. There is very difficult, it's basically impossible to form a correlation and say, I've tested this and therefore this alternative should be fine. But in some cases, we need to assume some sort of correlation, or more likely, we're going to do a risk assessment. So as fire engineers, we're quite often given limited information and told we need to evaluate what is the potential frequency of fire and what is the consequence of that. And generally we do that in qualitative terms. So I said I wasn't going to have a video. I didn't lie. This is just a photo of a small-scale fire test a facade scale test, an AS 5113 test at Exova in Dandenong. So it consists of what we'd call approximately a 3 megawatt or about a 3 meter cube wood crib. We ignite that with methylated spirits and we see how far the fire goes. We also measure temperatures through the wall, behind the wall, and we look at where the flames get to. Now I've just shrunk that down and compared that to an actual fire. So this is about 3 stories and this is about 3 stories on an actual facade fire. This fire is so large, it's creating its own weather. This fire doesn't have a return wall like this one, so you've got exposed radiation surfaces reheating each other, and nonetheless, this fire is large enough. The flame is spreading horizontally upwards. It's dropping debris. Maybe it's burnt out in these lower areas, but it's still going strong up here. It's just ignited up here. So this fireball is moving up the building at an accelerating rate. Even these effects are not captured by the largest facade scale tests that we can actually economically do. So we have a problem when we use combustible facades. And if you take away nothing else from this presentation, please be mindful that any combustible element in the wall needs to be looked at with caution and needs to be evaluated by a fire safety engineer. So I thought I'd turn to now what has the various states done in response to the various cladding fires around Australia. And generally it's a ban going forward on using aluminium composite panels with certain percentages of combustible core. In most cases, that's a 30% combustible, 70% non-combustible core is the cutoff, and any more combustible than that is unacceptable. And most states are also banning polystyrene. But this isn't a blanket ban on performance solutions generally. WA has actually gone to that level for certain types of ACP. Tasmania, sorry, there's a point missing in that slide. Tasmania requires I think it's the building minister needs to approve any use of these products. But there is still generally an acceptance that fire engineers can work with other combustible materials, but there are some explicitly banned from being assessed by fire safety engineers. There are various mechanisms in different states, and I don't have time to go through them all. The Victorian jurisdiction where I'm most familiar has the Building Appeals Board. It's also the state that's taken the most ownership from a governmental level in terms of identifying the scale of the problem and fixing it themselves. New South Wales and Queensland have effectively told people to register their own buildings, and then the council will be in touch with a building notice and tell you now need to fix your building. I've left some links in here. I'm hopeful the slides will be shared if you want to have a little bit more on most of the states around the country. And also at the federal level, the Australian Building Codes Board, who publishes the Building Code of Australia, in 2016, in response to the Grenfell fire, they issued an urgent amendment to the code. They completely changed the sections that dealt with combustibility of external walls. They consolidated them, they simplified the language, they clarified what acceptable bonded laminated materials were, and they clarified what ancillary elements were acceptable. They got rid of this word attachment because it wasn't really clear what was an attachment and what was part of a wall. Once you attach something to a wall, does that mean it's part of the wall and therefore should be non-combustible? It also introduced a verification method that facade scale fire test I showed you a few slides ago, that is brought up under the CV3 verification method. If you want to install a combustible material, most states will require you to have done a facade scale test with AS511 and also comply with the other parts of CV3. So then we got the BCA 2019. We're back to a regular 3-year update cycle. That was from 2020, the allowed sarking, which is a membrane that basically has to do with weather protection. Generally, these sarking materials work best if they're a little bit combustible, because the plastic materials that are used for the best sarking materials, they are plastic and hence combustible, but nonetheless very important for a modern building to avoid problems with mould, weatherproofing issues, etc. And similarly for windows, thermal breaks are allowed, otherwise our buildings would get cold. There was a new fire safety verification method which aims to change completely how we do fire engineering. It's technically been adopted, although we're yet to see widespread use of it. And there was a very good initiative. I'm not saying these other initiatives aren't good, but sprinklering all low-rise residential buildings is probably one of the best changes the ABCB has made, and that will have a massive improvement in fire safety around the country. More recently, there were still some changes to be made to the BCA. I think my previous slide should have said 2019 for the applicability date of the BCA 2019, by the way. Amendment 1 came into force halfway through last year. It now introduces a term that will be familiar to most fire engineers, which is a performance-based design brief. But say if you're a mechanical engineer doing a JV3 alternative solution or performance solution, you now need to prepare a performance-based design brief. Similarly, if you're doing an accessibility performance solution under D3, you need to do a performance-based design brief. So that's effectively, you're telling everyone, this is what I want to assess. Do you agree? This is how I'm going to assess it. Do you agree? And then you go off and do your assessment. There's also changes to the concessions for timber low-rise buildings. And there's a helpful cheat sheet right at the end of the BCA that tells you what amendments there are. So for a facade system to be combustible, there are 3 options. I won't go through each of those except to point out the third. For certain materials, we actually can't even do that in WA without the Building Minister's approval. Please talk to fire engineers early and often. And the main final point I wanted to say is, here's an example de-identified of some shop drawings that we were sent for a remediation of an existing building. It's a low-rise building. It has timber framing. We're replacing all the polystyrene with a non-combustible material. Now, ordinarily, this sort of project wouldn't even pass the desk of a fire safety engineer. But these notes are really just to illustrate the benefit a fire safety engineer can add to a cladding rectification project. Even if the intention is to get as much steam to satisfy as possible, a fire engineer can help you interpret the code and give the building surveyor some confidence that that's actually going to be met at the end of the project. I won't go into that into detail, except to point out there is a guide for all of this for fire safety engineers. And there are a lot of issues around facades, combustible facades. We're seeing skyrocketing insurance premiums where not just consultants, but owners are left with a monopoly on insurance and a monopoly on engineers who can actually help them fix their problem, because there are only a few engineers who actually have the insurance to do this kind of work. We're really seeing the unintended consequences of these complicated buildings, and perhaps we need to return to a bit more of a simple approach. We need to avoid introducing new issues, and leaky buildings is one I want to highlight. Every week, it seems, I read a news story out of New Zealand where buildings that were built 10 years ago won architectural awards, maybe 15 years ago before the code was tightened up, and have to be demolished. $1 million properties basically are completely worthless because they've captured moisture in the cavities and they've developed mold. So we need to avoid replicating these problems. So that's probably past my time, but I'll pass back to Amanda to introduce the next speaker. Thank you very much.
I'd now like to welcome our second and final speaker for today, Cathy Inglis. Cathy has worked for Brickworks for over 24 years and has been pivotal in the development of some of Australia's leading facade systems. Highly respected authority on various building products and systems, Cathy has a Bachelor of Materials Science and a Master of Science, and is also a National Director at the Housing Industry Association, which represents the industry on several Australian standard committees. Cathy will offer an overview of regulations related to non-combustible facade, the impact these have on design, and explain some of the notable facade systems which she has helped to develop. Please welcome Cathy Inglis.
Good evening everyone, and welcome to another Engineers Australia event. My name is Cathy Inglis and I'm the General Manager of Technical and Innovation at Brickworks Building Products. Thanks Blair for your great presentation, and now I'm going to continue and explore non-combustibility a bit further. I'm going to specifically look at fire testing, show you examples of the testing and of products that fail and pass the non-combustibility test methods. So as you know, there's a long history of cladding fires around the world. But this really hit home when we had the Lacrosse fire in Melbourne. This was way back in November 2014, and yet it took up until 2018 for the Building Codes Board to introduce regulation into the NCC to address fire safety in buildings. So there's a long history, even going back in Australia. There's a motel fire in Albury in 1999 where the external facade was a fiberglass cladding. The fire started on the 3rd floor and quickly escalated up the external facade of the building. The Tirapa Museum in Wellington. This was a project that was constructed with aluminium composite panels and had extruded polystyrene insulation. And during construction, a welder ignited the insulation and it quickly spread a fire up the external facade of the building. The third photo shows an apartment building in Munich in 1996. And this building was a heavy masonry building but had an insulated insulation on the outside of the building, and this insulation was combusted and caused the fire on the external facade. The Fire Cones Reform Report was commissioned by the Australian Building Codes Board and completed in 2020. This report addresses the safety and fires that have occurred around the world and in Australia. And this was completed, as I said, in 2020, but yet there was no action taken to address and change any measures in our building regulations. Until following the Lacrosse fire in 2018, March 2018, the NCC put an out-of-cycle amendment in to address the serious issue of fire safety. And this measure came into effect for Volume 1, classes 2 to 9 buildings only, and for Type A and B construction. And this now required those to be made with non-combustible materials. So the performance requirements of the NCC. So you've got Performance Requirement 1, where a building must have elements which will, to the degree necessary, maintain the structural stability during a fire. Performance Measure 2 is that the building must have elements which will, to the degree necessary, avoid the spread of fire to exits, to sole occupancy units and public corridors, between buildings and within a building. So these two performance measures is what governs the rest of it. And these performance measures are also applicable to the type of building. So that takes into account the height of the building, the number of exits, the time to escape, what fire measures they have in the building, and a whole list of things. So the C1.9 is the specific clause that talks about the non-combustibility of building elements. So in a for non-combustible building elements, in a building required to be Type A or Type B construction, the following building elements and their components must be non-combustible. So that's the external walls and common walls, and all components incorporated in them. The flooring and framing of lift pits, and also non-load bearing internal walls that are required to be fire resisting. Also required non-combustible building elements for shafts, for lifts, ventilating pipes, garbage, chutes, etc. And these are required to be non-combustible as well. However, there are some exemptions for products that don't have to be non-combustible that are included in those walls. And this list is quite long, but includes things like gaskets, caulking, sealants, termite management systems, glass, thermal breaks, and damp-proof courses. Then there's also a list of materials that are allowed to be used where a non-combustible material is required. So these include plasterboard, perforated gypsum, fibrous plaster sheet, fibre reinforcing cement sheeting, pre-finished metal sheeting that has a surface finish not more than 1 millimetre, and also the spread of flame index not greater than 0. And also exempts sarking type materials that aren't more than 1 millimetre in thickness and have a flammability index not greater than 5. Now these two lists are quite extensive, and are not inclusive. There's a whole lot of other things that you put into an external facade that aren't covered. In the amendment coming up for the NCC 2022, there's going to be an amendment to this section of the code, and this is going to allow a lot more exempted items in these lists, and that will include things like wall ties, screws, fasteners, connectors, clips and brackets. It will also include articulation joints and packers and shims. So they're proposed to be added in 2022 amendment. The amendment draft is coming out in May this year and will be open for a 2-month public review period. So if you're interested in that, please have a look at that and you'll be able to make comments on that. There are obviously things that there's always things that they're not going to be able to cover, but at least that list is now continuing to have some more common materials that need to be excluded because there aren't non-combustible options for them. So the other part of this clause is bonded laminate materials. So bonded laminate is able to be used where you need a non-combustible material, as long as each layer of each laminar is non-combustible, that each adhesive layer doesn't exceed 1 mil in thickness, and the total adhesive in the product is not more than 2 mils overall. But it also must have a spread of flame index not exceeding 0 and a smoke development index not exceeding 3. So basically a bonded laminate, that's like the Vitricor G2 type products. So to meet the performance requirement CP2 for non-combustibility, there's several compliance paths you can follow. So the NCC being a performance-based document, you can do a performance solution, or you can do a deemed to satisfy solution. So a deemed to satisfy solution is where you can use a non-combustible cladding. So that is a material that's known to be non-combustible, concrete, bricks, glass, etc. Or you can use a material that is tested to AS 1530 Part 1 and demonstrate that it's non-combustible. So if you can't do either of those things, you can use one of the materials that is deemed non-combustible in that list of exemptions that we just discussed before. So often we get asked, bricks, concrete, they're not listed as exempted materials. Why aren't they listed? Well, they're actually known non-combustible materials. And finally, in the amendment coming out in 2022, the NCC is actually going to list those materials and going to list that they are known non-combustible materials, and that's going to include concrete, steel, masonry, AAC, aluminium, concrete and terracotta roof tiles. So they're now all going to be listed as non-combustible materials, so you won't have to ask for testing. Because surprisingly enough, a lot of people ask for testing to AS 1530 Part 1 for a brick. Now, just as an aside, when we make bricks, we fire them at over 1100 degrees. And so they are made with fire. So they are all non-combustible by nature of their manufacture. However, we still get asked for it regularly. So to now go into a bit more depth on the testing and show you what it looks like. So AS 1530 Part 1 is the non-combustibility test. And this is where you take a sample that's 50 mil in diameter, approximately 50 mil deep. You drill a small hole in the centre which a thermocouple goes into, and it sits in a basket. So as you can see there in the photo, there's a small sample, it sits in the metal basket. It's then dropped into a furnace at 750 degrees. So what you can see there on the right is at the top there's a mirror so that the testers can see into the furnace to see what's happening. And essentially the sample is dropped into the furnace and placed there. So you pass this test if you have no development of flame and your sample doesn't exceed a certain temperature rise when it's immersed. So that's what it shows like when the sample is going into the furnace. If you have a product that's not thick enough to be 50 mils high for the sample, you take layers of it and layer it together, as you can see there. It's dropped into the furnace, and if there's no flames and no too high a heat elevation, it will pass. However, if there's flaming like you can see now, these samples would have failed, and that's what a failed sample looks like. When you put an aluminium composite panel, the type that Blair was talking about before with the polyethylene cores, they don't even make it to inside the furnace before they actually ignite. When the products are tested, you get a test certificate. So at the moment, there's a couple of registered authorities that will do this testing. You've got CSIRO and also Exova Warrington Fire, and that's what the certificates would look like. And they basically end up deeming that your product is deemed to be non-combustible. So looking at the other fire tests that we mentioned before for sarking type materials, and for bonded laminates, where AS 1530 Part 3. So this is a sample where you put the material in a test rig and you gradually bring the heat source closer to it to ignite. And this will provide the following indices for smoke development, the heat evolved, ignitability, and also the spread of flame. So as we mentioned before, a bonded laminate can't have a spread of flame not exceeding 0, and it can't have a smoke development index of greater than 3. So this is the test you do for those sort of products. AS 1530 Part 4 is a full-scale fire test that gives you the fire resistance level. And this is the component of 3 things: the structural adequacy, the structural integrity, and the insulation properties of a product. So when you test to this, it's a 3 by 3 metre wall, and you build up your wall and test it in a rig, and you get a fire resistance level number. And this number is given, as I said, in the 3 components if it's load bearing. If it's a non-load bearing test, you would have a dash 60-60 or dash 90-90, and it's all rounded in 30-minute increments. When you do a fire test, it then gives you the option to do variations, so you can get different configurations from that assessment report, and they're done by the experts at the fire lab, and they're considered valid to use as a performance solution. So looking at what happens in the fire test, it goes to 1100 degrees on the inside of the furnace, and you can see there on the left, that's a brick wall that's been pulled away after testing. You can see how hot it is. And on the right is a wall that was a panel test that has failed, and you can see there that one of the panels spanning has collapsed. So when you put a fire source next to a wall, the wall will bow towards the fire, and eventually it will collapse depending on its integrity. So that time will give you the first fire resistance period for structural adequacy till the time where the wall will collapse and no longer maintain its structural function during a fire. The changes that came into the NCC with the fire, when the fire measures came in, they added an additional verification method. So this verification method is to demonstrate compliance with Performance Clause 2 to avoid the spread of fire. So this is an external wall test, and this is tested to Australian Standard 5113. And when you test to this, if you achieve the EW rating, then you can use that system as a product to meet the requirements of the NCC for non-combustibility. However, if you use this as your measure of compliance, there are some additional things you've got to do, such as additional requirements for sprinklers, etc., that are required. Now, this test is a full system test. So it's a fire spread via external walls, and it's very similar to the British test method, but this is fire propagation testing and classification of external walls of buildings. So this is, as I said, a system test. It's a wall built up in layers, and at various heights of the wall there's a series of thermocouples and various through the thickness of the wall there. So you can see the positions of the thermocouples shown there. So this wall's about 9-10 metres high. You build up with your internal frame, your insulation, your internal lining, right to your external facade. And on the right you can see a test rig that's set up ready to be tested. This test must include a return wall, a wing wall, and then there's a chamber at the bottom for the firebox and fuel load to be put into. And that fuel load's sort of roughly the same as a lounge that would be combustible, that's made with man-made fibres. So when this test happens, they ignite the fire source at the bottom, and as you can see, the fire continues to burn. The fire source eventually falls down and will just extinguish. So it runs for basically 30 minutes. This test here was a product that has passed it, and we undertook this test. This is a magnesium oxide board that actually passes 1530 Part 1 testing. But we thought we'd try this test because a lot of people were saying a few years ago that products will not pass this test, it's too severe. However, we gave it a go and tried this, and it was actually all very boring in the end. All we ended up with was a bit of smoke on the wall once the fire was extinguished and put out. The results for the test, there is 9 criteria that you have to meet to pass this test, and you have to pass all of them to get the EW classification. And this relates to temperature at certain heights of the wall, temperature at certain positions, and a certain rise, that there's no flaming, there's no opening, there's no spread beyond the specimen, there's no flaming debris, and there's a maximum debris amount of less than 2 kilos. So if you can't pass any of those, then you will fail an external wall test. When you then, following that, when you dismantle your wall, you can see there that the firebox is removed, the external cladding was taken off. You can see the brown staining on the sarking, and then, but when we've removed that and you can see the insulation and timber framing behind that, you can actually see that there's no damage through it. So that's a wall that passes. Now I'm going to show you some examples of some other products testing that don't pass it. So what you can see here is the AS5113 test of an aluminium composite panel. Now on the left, the fire started. That time on that one, you probably can't see it, it might be a bit too small, but it's 4 minutes and 34 seconds. And at that time, you can already see that the aluminium is starting to burn. The photo on the right, it's extending up and growing bigger. That's at 5 minutes and 55 seconds. This test was stopped at 10 minutes 21, where the whole panel, as you can see in that photo, is now essentially burnt and disintegrated. But it's not just the panel itself, it's right through the wall system that has actually burnt and failed at 10:21. So looking at another test, AS5113 again, but with fibre cement boards. So this test was constructed with 9mm fibre cement boards. Again, fire started, you can see on the left, this is a 9mm FC sheet. The fire went through. These photos, they're not very clear, but this shows the back of the wall after the test was stopped. And this shows that the fire on the right, you can see the red glow. That's where the fire actually came right through the fibre cement boards, through the frame and insulation and through the plasterboard on the inside. But as you can see on the left image, there's the fibre cement boards, there's not a lot left of them. What happened, and it started happening probably about 10 minutes in, that the boards start to crack and pop and they explode off the facade. So that product, interestingly, is deemed to comply for where you need a non-combustible product. The NCC then added also auxiliary elements and a bit more description around these, because this is where we ended up with a lot of the aluminium claddings that are combustible on buildings and the EPS. People were calling it an attachment to the building because you are allowed to have a non-combustible attachment. So now the NCC has really tightened up on what those non-combustible attachments must be. So you've got a list of exempted items: gutters, downpipes, flashings, grates and grills, electrical switches, light fittings, signs and awnings. But there's now a limitation to the size and placement of these objects so that not to cause issues for egress or fire to enter the rescue to enter the building. A couple more examples of photos. We undertook some testing, some small scale, I suppose you'd call it pilot testing, 5113 rig, where we built brick walls next to other products. And the one on, this is for polystyrene, a polystyrene EPS cladding. And what you can see here is at about 7 minutes, the whole EPS cladding just fell completely off the frame and fell to the ground and continued to burn. And the bottom right-hand photo, you can see there that the brick's still on the left, but basically nothing left of the frame or the insulation where the polystyrene was. Looking at another example of that, this was a fibre cement, a 6mm fibre cement sheet, again with the fire source going up. And what you can see there is cracking that has occurred in the fibre cement sheet. And you've also got, if you look at the photos that show from the rear of the wall, it shows the flames and smoke coming through those cracks in the wall. So to demonstrate compliance to the performance measures, there's 5.2 in the NCC gives you evidence of suitability and gives you the steps of how you demonstrate suitability, starting at the highest levels using code marks, certificate of conformities, certificates of accreditation, testing certificates issued by a certification body, test reports by accredited laboratories, and right down through going down the list of hierarchy down to certificates or reports from professional engineers, appropriate qualified persons, and to a product technical statement. So depending what you're talking about, needing to demonstrate suitability to, which level you'd want to pick out of those. And something that's more critical and more of a risk, you would escalate it higher up the level to demonstrate that element and evidence of suitability. So there's more to this than non-combustibility. And when you're doing an external facade, non-combustibility is just one component of it. And the other things that have to be taken into consideration: appearance, structural integrity, serviceability, waterproofing and condensation, thermal and solar transmission, acoustic properties, sustainability, and also durability. Facades over the years, there's lots of incidents where there's been failures from other things that have probably had more research and testing put into it, structural adequacy, durability, etc. But these all have to be maintained as well and complied with. Interestingly, I mentioned before that the changes for the NCC coming in for 2022 come out in May. In July, the changes for the NCC 2022 for energy efficiency and for condensation are coming out as a separate amendment. And that the reason they're putting them as a separate amendment then is because of the amount of changes that are going to come into play for energy efficiency and condensation. So keep an eye out for that. So now just to give you an example of a couple of products that can be used where you need a non-combustible material. So Brickworks have a terracotta cladding system called Terraced. So this is a fired clay tile. And as I mentioned before, when we fire clay, we do it at over 1,000 degrees so that they will always meet the non-combustibility requirements. But we do have a test certificate anyway. We tested it just in case. I got sick of people asking me, did we have one? So I finally ended up testing it, even though we manufactured it over 1,000 degrees. So it's a lightweight terracotta tile facade. We have two systems, one that hangs on a vertical steel rail, one that hangs on an aluminium horizontal rail. And both of these tile systems can be used where you'd need a ventilated rain screen facade and come in a huge range of colours and textures and sizes to give you lots of options for construction. So just to give you show you some examples to finish off. For a reclad, I know Blair talked a lot about recladding of buildings. This is where the product's been used to reclad a building with a combination of different colours on a building. Looking at the build-up of the Terraced XP product, you can see there the tiles hanging on the aluminium rails with the sarking onto a concrete. This is a concrete framed building in the background, which was the University of Sydney building on campus there. The other thing about these products is they can be prefabricated into modules and then attached to the building afterwards. So this is a project in Adelaide where we actually prefabricated the panels into modules. They were fixed to the building with the rails, so that you can see the aluminium rails fixed to the board, and then finally the tiles were hung once on site. The Sydney University photo that I showed just prior, some parts of that were prefabricated with the tiles into modules in Thailand. They were put in containers, brought to Australia, and then put up on the building. And when they did that, I think they broke one tile in the whole process of that. So they're fairly rigid and not impact resistant in that way. So this is the final building once the tiles had been hung on it. And it's a hospital in Adelaide, St Andrew's Hospital. And as you can see now, that building looks fabulous with the terracotta cladding. Obviously comes in a wide range of colours, not just terracotta. But the good thing about the Terraced is that it comes with a 100-year product warranty. So I know there's a lot of concern from people worrying about what future changes are going to come into the NCC, how that's going to affect if something does change. So Brickworks offers a 100-year warranty for Terraced and a 20-year warranty on the system. So Terraced comes with that 100-year product warranty, so you can feel safe that we will back your product from Brickworks, and it has a 20-year system warranty. So thank you very much for your attention, and thank you for listening. Now I will hand back to Amanda for the Q&A.
Thank you for two great presentations. Our speakers will now come together, Blair and Cathy, and take questions from you, our audience. It's your turn to get involved. I also want to thank everybody that sent questions through on registration, and we might start with one of those. And the first question I have is, give Cathy a rest, is for Blair, and this has come in from Tumas, who's based in Queensland. Good evening, Tumas. And the question is there a trigger point when combustible cladding must be removed above a certain quantity in relation to the building size? Does fire extinguishing systems affect the criteria? Thank you, Tumas.
Thanks, Tumas. So I guess that could be another 1 hour presentation. In Victoria, I've sat on hundreds of panels for buildings that have been found by the Victorian Building Authority in their inspections to have combustible cladding. Now, that might be a bit of aluminium composite panel on the awning on a shop front on an otherwise completely non-combustible external wall building, or it could be a building that looks like it's going to be the next lacrosse or somewhere in between. In Victoria, all of this information is gathered by the VBA, and as a rolling process, a panel of experts is convened, a fire engineer, fire brigade officer and a building surveyor, and they rank the risk of the building using some predefined criteria. Any building that comes into this process is non-compliant. It should never have been built using those products, and all of them will get a building notice from the council to rectify their non-complying buildings, and then it's up to the owners to deal with that. And I believe broadly it's similar in every state. It just, the manner of that reporting is a bit different. In some cases, it's a self-reporting mechanism, and if you're found not to have reported your own combustible clad building, then you'll get a massive fine from the regulators. But they're putting the onus on the owners to do that work. So the risk assessment process is really triage. Where should we start fixing buildings? But then each individual building, to justify retaining some cladding, needs a state legislation that allows that to happen. In some cases, that's not possible. And it also needs a fire engineer who has insurance to do an assessment, and a certifier or a building surveyor who has insurance to accept that assessment. So what happens is fire engineers are now becoming very, very conservative, and building surveyors more so, because no one has the insurance to accept any of this anymore. So we're finding that even things that even 3-5 years ago we could have justified, we're finding fire engineers are saying is not acceptable. In terms of extinguishing systems, we've seen some fantastical, almost George Orwell type creations of, H.G. Wells type creations of a robotic arm that comes out and sprays water at the building. None of those have been implemented to date, as far as I can tell. Internal sprinklers, if you've already got them, great. If you don't already have them, by all means put them in, but they're not going to stop a facade fire. Well, they might stop it from becoming a full building fire if you're very lucky, but they're not going to stop a facade fire growing and spreading up the building.
Thanks, Blair. And from Queensland, we'll go to South Australia, and this is a question for you, Cathy, that's coming from Dean. And Dean's asking, how do you see concrete-based products such as glass reinforced concrete being part of the solution to this issue?
Thanks a lot for the question. Glass reinforced composites can work in with it. Obviously, they've got to pass one of the test methods because they're not deemed to satisfy materials. So either passing 1530 Part 1 or 5113 or being part of a performance solution. So the glass reinforced cement, so the example I showed of that 5113 fire test saying it was a magnesium oxide board, that's actually a fibre reinforced cement panel. Now, obviously, they've got to be used in the right applications and the right products, but there are ones that could potentially pass that test if they're tested.
Thanks, Cathy. We've got a question that's come in tonight from Mario, and Mario is from VDM Consulting Engineers. Good evening. Asking Blair, in Australia, there are overseas materials that come certified, but those certificates are not genuine. How can we certify something that we're not sure whether it's genuine or not? Great question.
Yeah, so I guess thanks for that. If it's been tested locally, obviously that's our gold standard in Australia. We think we're better than everyone else, and our test labs in general are accredited as a laboratory and also to test individual tests for fire safety and other building tests. So if you've got a NATA accredited laboratory who's done a NATA accredited test in that laboratory, then you've got a pretty, you can be pretty comfortable that the test result is genuine. Overseas labs have an international agreement between NATA and what's called ILAC, the International Laboratories Association Council or something like that. And there's agreement between those different countries under that umbrella agreement. And so our building code actually recognises that mutual recognition between Australian and overseas test labs. So if you've got a French or a Singaporean or a Chinese test certificate, then that is probably going to be okay as long as the lab was accredited by their local body and that body was part of ILAC. In terms of telling whether a material is genuine or not, that I guess is a very, very difficult question. It's probably an episode of Border Security rather than a Engineers Australia talk. But if you're suspicious, then I guess you could take a cigarette lighter to something that said it's non-combustible, and if it flares up, then you've probably got a problem, and then you can take investigations from there. But really, talk to a fire engineer or a test lab if you've got concerns on a particular product.
Thanks, Blair. And just stay where you are. Bill sent in a question talking about mineral core. Mineral core is now banned. ACPS has fire retardant properties. However, all legislation ignores this. Past colleagues and CSIRO have papers on it. Would you like to comment on the comment, Blair?
Yeah, so when we talk about aluminium composites, we've found 3 or 4 different flavors of core, I guess. There's if you cut it open, you'll find either a black core, a white silver core, or you might find a corrugated aluminium, which is more, effectively these are the only materials that are used these days. So historically, the signage boards that then got turned into facades were pure polyethylene. That's the black stuff. It's basically compressed cling wrap. The stuff you'd wrap your kids' lunches in has been recycled out of landfill or whatever. It's turned into a building product and sandwiched between 2 thin sheets of aluminium. That's the stuff that burns really, really well. When manufacturers in Europe and Japan and the United States first found out that they needed to pass certain combustibility criteria, they then started dosing the core with a mineral fibre. Minerals such as calcite or brucite, magnesium hydroxide, aluminium hydroxide, or an inert product such as calcium carbonate, limestone. And they found that 30% was really the magic number. We had 30% combustible polyethylene by mass, 70% non-combustible. You could pass the tests that were being done at that time. So NFPA 285 was one of the first facade tests developed in the 90s. You could pass that with a 30% combustible, 70% non-combustible core. As we move to more comprehensive facade scale tests with a wing wall, with a larger fuel source, we find that you can't pass these. I'm not aware of any fires internationally where a 30% combustible core has actually been the cause of a multi-level or a multi-compartment fire. I'd be interested to see any case studies if there were. But nonetheless, Victoria has actually gone further than the 30%. They've banned everything, even down to, I think it's 8% combustible is the cutoff. So you have to be almost completely non-combustible before you can have 8% polyethylene in your core. And so this is based on risk assessments, but it's also based on, having safety factors on things. It's based on the fact that if you do one test and you find you're 29% combustible, you might find the next one is 31%. And they just wanted a huge safety margin there. But it's not necessarily borne out by risk statistics. It's really borne out by what passes these tests that we now accept, and we go from there.
Thanks, Blair. We've had a question come in around cost, and this is directed to you, Cathy, from Hing Chung in WA, asking, how high of the cost to construct non-combustible facades compare to the conventional facades?
Well, it really depends what you build it up and what your layers is and what the building is. You can still have some very cheap non-combustible facades, back to your traditional materials, concrete, masonry, brick, precast concrete, very basic stuff. They're all non-combustible and can be used. Getting into, and Blair talked in about his presentation about why the ACPs were picked for their lightness, colour, ease of applying them to buildings, but also that they would make a cheap, lightweight facade. So the ability to do that now, they're probably, if you change from an ACP to a solid aluminium panel, they're obviously going to be more expensive. But there are still ways you can do it. But if you just replaced a composite aluminium panel with something of the same size and same colour in a solid aluminium panel, it's going to cost more on the project. But there are still options to get cheaper facades using the more traditional buildings materials.
Thanks.
And can I just add something that just on the question before on test and test certificates and knowing if they're genuine. One of the good things to do, there's a lot of editing goes on certificates that may be available. So someone has done a genuine test to something for a product, and they can be quite easily manipulated now. Everyone's got Adobe work, you can manipulate things. So if you're provided with certificates, it's always good to check back through websites, but go contact the labs. I've seen some certificates, and I've contacted the labs overseas, and they've said, no, these products have never been tested here. They've, don't exist. So that's a good place to start. I'll just add that to what Blair said before.
Thanks, Cathy. And staying with you and grouping a few questions together, and moving to the standards that we're being asked, and I'll use Mario from New South Wales as example. If the facade material comes from overseas, how can we make sure that it complies with Australian standards?
So if you want it to comply with an Australian standard, it has to be tested to an Australian standard. But if you've got, as Blair said before, testing to an overseas laboratory, the fire engineer can do a comparative assessment between a test done in a French or Singapore lab back to the Australian standard fire test. The British external facade test is it's just about the same as the AS 5113, so they can be done and assessed. But if they're tested in Australia to a NATA, in a NATA accredited lab to a NATA accredited standard, then you've got that, and that's a very easy thing to check with those laboratories whether that certificate for that product is real.
Yeah, as David Brent would say, different frogs, different times. They need to be substantially similar tests to be able to allow any sort of cross comparison. It can be done. It's difficult. You need a fire engineer who speaks French, which I don't.
Yeah, and can translate the reports, of course.
Yeah, that's important.
And sort of sticking with that theme, the question's been asked quite directly. So, if every building is every building material tested by government or body corporates before use in buildings? Blair.
Broadly that's the case. In Australia, the test labs are privatised. NATA, the National Association, that's a government-run authority, I believe, or possibly it's funded by the test labs who are members. I don't actually know that, but certainly the test labs are private entities, some of them government owned, but they operate as private businesses like CSIRO. So yeah, broadly, every material you want to use as part of the building must be tested in accordance with the standard that's referenced by the Building Code of Australia. And in fact, a fire engineer like myself, we might be asked to justify part of the building not complying with the deemed to satisfy provisions of the code. We might require a higher level of performance for certain materials or additional testing on the materials to offset some other fire safety problem that we're trying to overcome. So having or someone on your team who understands the building code and also is able to read the fire engineering report and interpret that is really important for every building.
Thanks, Blair. And just staying with you, we've had a great question from Gerard, who's in WA, asking, he says he'd like to know what sort of risk assessment approaches people are involved in just now for making decisions about whether to replace ACM cladding with NC products on higher risk buildings.
That's a really good question. So at a government level or a portfolio level, what you want to use is a triage tool. So in Victoria, the Victorian Cladding Task Force that was set up after the Grenfell Towers fire, they developed a risk assessment tool. And what that does, it ranks, you identify properties of your building, the height, the number of people in it, the types of cladding materials, is it continuous, is there a sprinkler system, these sorts of things. You plug that into a spreadsheet and it'll tell you your low, moderate, or high or extreme risk. And that tells you where do you start applying funding to fix the problem. And in future, maybe you decide that anything that falls in the low category, here is my acquittal criteria. Here's what the council needs to make sure happens before they can say, right, the building is now safe to occupy. It allows you to make decisions at a government level about, say, an extreme building. The government might fund urgent rectification to that, understanding that some people in these, especially the 3-story, 4-story polystyrene buildings in outer suburbs, they tend to be some of the least well-funded owners corporations with the worst cladding problems to fix. So Victoria has actually put $600 million aside to fix those extreme risk buildings, and the government will actually pay for that. So if you're a portfolio owner, say a Green Rock Investments Corporation, and you had 1,000 buildings, you might use a similar triage tool to say, where do I start applying this? The NFPA effect tool that was developed by ARAP and the National Fire Protection Association, US, that's a similarly very good starting point for triaging your portfolio. But you can't use that tool to design the rectification for an individual building. That's where you need a fire engineer to actually look at, okay, for this building in front of me, if I imagine where a fire could start on any of these facades in the cavity or in an apartment, what is the likelihood of that happening, and where will that happen? So that's a completely different type of risk assessment. It's a qualitative risk assessment. We might do some quantitative fire modeling for that, but generally it's a scenario-based risk assessment. And we'll use that to determine, okay, if we remove this amount of cladding, as a fire engineer, do I think that will stop fire from spreading and having a catastrophic outcome? And so for that, we use a risk matrix to come up with an acceptable level of rectification. Again, I could probably talk about that for a couple of days, as you can probably understand. It gets me quite excited doing that kind of work, but don't have time for that.
Thanks, Blair. Maybe we'll do another webinar on that.
Sure.
We've had a question coming, Cathy, from Dalton in Queensland, direct to you, asking, how do tiled facades fit into the building code? Tile adhesives won't pass AS 1530.1, but are often sufficiently protected by the tile. Testing a full system isn't practical, as the system requires retesting once the tile changes. Cathy, thank you.
Yes, it's definitely impractical to test every system you'd have with putting a tile on a facade. And usually if you're putting tiles on with an adhesive, underneath that would be a solid concrete brick masonry structure of some sort. You're not going to be sticking tiles onto, well, I hope not, onto expanded polystyrene or something. But unfortunately, the way it's written, adhesives don't have an exemption as an exempt material, and they're not in the new list of ones that are coming into the 2022 NCC. So that means that your use of adhesives for tile fixing is limited to certain areas unless you can get it approved as part of a performance solution for the overall wall under the verification method in the NCC. That'd be the only way you could do it.
Thanks, Cathy. We've had a question come in from Paul, and I know, Cathy, you're keen to answer this question, and apologies if I mispronounce this. So we've had a question from Paul that says, so Vitricor's product as a spread of flame index of 0? Question.
Yes, it does. So as Vitricor is a bonded laminate, so it does have an exemption to be able to use where you need a non-combustible material, as long as that bonded laminate that if has the adhesive layers individually no greater than 1 mil, combined less than 2 mils. So how many layers there are? Can't be more than 2 mils, and they still must have meet that requirement for spread of flame and smoke development as well, and then it can be used. So Vitricor does meet that. I've sort of, sometimes you see a sample and you look at it and go, oh, that glue layer is quite, how good's their manufacturing to keep it under 1 mil? I believe now they've improved that a bit because the samples I've seen lately are looking, closer to that. So that it's just one of those things you've got to make sure that what you get as a sample is what you're going to get going forward, and you can meet that clause in the C1.9 D. Which one? I forgot the number now.
C1.9 E6.
Yes.
Roman numeral 6.
I know, yeah.
On page.
Thank you.
Do you want to expand on that a little bit, Blair?
Look, I'll just point out, so Vitricor is a brand name. Full disclosure, I've done work for Fairview, who produce the Vitricor and Vitribond range of panels. Their first generation of aluminium with a bit of glue laminate panels. That was, I think, Dab applied in the manufacturing process on a sort of a hexagon grid in the middle. If you pull it apart, the glue looked quite stretchy, and there was definitely a question about whether that was less than a millimetre in any layer once you pulled it apart. But of course, you pulled it apart, you've changed the mechanical properties. So more recently, they actually use a continuous roll of adhesive film that, when it's bonded together, it starts off with, I think it's about 50 microns, and when it's compressed, it's no more than 100 microns, even in the compressed parts. So where it's squeezed out like a tube of toothpaste. So I think, as Cathy said, they've overcome those issues.
Thanks, Blair.
Yeah, they have, and I think sorry, I shouldn't use a brand name, but there's obviously a group of products that same sort of classification, but that's the name I know the most. So yeah.
Yes, someone had a question about Alpolic NC, and I believe that's a similar product put together in a similar way and classified under the building code as exactly the same thing. It's what we'd call a deemed non-combustible material. So it's a material that if you pulled all the layers apart and tested each individual layer in that AS 1530 Part 1 test that Cathy showed us earlier, the glue is combustible. It's a polyurethane glue, and most definitely would fail that test. But the BCA says, well, yeah, but it's a low risk when you put it all together and you have it in large scale. There have been large facade scale tests on those sorts of products, and they routinely pass. They don't exhibit flame spread behaviours past the initial fire source. So they're low risk even if they would fail the initial screening test. And that's the point of fire engineering. We keep testing things until we've broken it, and then we assess, okay, what did we break? Is that an acceptable level of risk, or is that unacceptable because it failed so spectacularly?
Thanks, Blair. And moving on to insurance, which is a very hot topic, excuse the pun, but we've been asked a question. Current insurance policies do not allow for the use of composite aluminium materials. Wonder if this will change again, given the NCC update. Blair?
Yeah, I don't think changes in the building code will make the insurance market happy about the state of engineering in Australia and New Zealand. So our market is kind of grouped Asia Pacific, and the insurance underwriters, who are mostly based out of London, they've received enough cladding especially, but waterproofing claims, Leaky Buildings from New Zealand, dodgy building surveying, certifying claims, those sorts of professional indemnity insurance claims, either an actual claim that's gone through litigation or been settled out of court for X amount of money, or they've been put on notice that, in 2013, we designed 150 buildings with combustible cladding. If someone comes and sues us, you need to pay because you're our insurer today. So the insurance market went through an absolute skyrocketing of premiums, and they also clamped down on what they were insuring engineers and building surveyors for. They put in what's called either a material exemption or a cladding exemption into the PI insurance policies. And they basically said, engineers, if you write a performance solution that justifies these materials and someone sues you, you're on your own. You're self-insuring for that risk. Governments then realised that we had a whole bunch of engineers without the proper insurance that are required under legislation. So rather than dealing with the insurance agencies or coming up with a government insurance scheme, they changed the legislation. So there's now no consumer protection if that actually happens. So the engineer will go broke, and the people with the cladding problem will have to fix it without being able to sue the engineer. It's been handballed from basically the insurance industry down to the engineers who have had skyrocketing premiums, and therefore they're passing it on to consumers or deciding to exit the market. So what we're finding is fire safety engineers, 99% of firms will not touch a combustible cladding or even a combustible material in an external wall. They will not justify it for your building. My firm's been, not been sued for any cladding matter or anything for that matter. We started in 2013, so touch wood, we're doing all right. But even our insurance premium is just astronomical, and we have to make very difficult decisions about, do we raise our rates or what do we do? Do we just turn people away? Realizing that if people have an existing problem, an engineer, a professional engineer who understands the problem, really needs to look at this for the good of society to fix these problems. We actually have a right back under our insurance policy that allows us to fix existing buildings without, and our insurers will back us to the hilt, but we can't justify a new combustible cladding product going forward. So we have to, again, make a very difficult decision whether to self-insure. And as far as I know, every other engineering firm is in the same boat. No one has a caveat-free insurance policy anymore.
Thanks, Blair. Cathy, do you want to comment on that from a manufacturer's perspective? Is there anything you'd like to add?
Yeah, I mean, we're at the same boat with supplying. Obviously, there's a couple of class actions going on against manufacturers and suppliers of the aluminium composite panels, and so yet to see how that plays out. But as far as a company like us, we actually don't have product insurance for anything that we manufacture that may not be to a particular standard or that fails on site. We back that from Brickworks. That's our warranty that we do from, being around for 100 years as a building manufacturer supplier. The cost of insurance, we could not afford to pay the insurance for the scale of what we have with 29 manufacturing facilities in Australia, the range of products, the range we sell. We couldn't afford to have specific product insurance. So we make sure, and one of my roles in the company is to make sure every product we sell to the market meets the minimum requirements of the National Construction Code, the relevant Australian standards, and is fit for purpose and meets our Brickworks minimum quality standards. And there's a very high bar on that. So anything that doesn't get there, we just don't go near as selling as a product. Straightforward as that.
Thanks, Cathy. And we've had so many questions, and I want to apologise to people that we are running out of time. We've almost run out of time. But there's that level of interest, and I'm sure we'll be doing more on this down the track. But I'd like our speakers to just sort of just take a minute or just 30 seconds just to sum up what you think is the most critical issues here with this topic, and how you think we're going to move forward in the future. And maybe I can start with you, Blair, as to what you think are the priorities to drive change.
So I guess we've got no choice but to use predominantly non-combustible materials, but we have to use some combustible materials such as sarking. We want to get back to being able to use good performing thermal insulation. We need more testing from manufacturers, and we need the manufacturers to work together to actually pool their resources and test composites. There's no point just testing materials in isolation when what we care about as fire engineers is performance of building materials, actual systems overall. You can't just test a doorknob, you have to test the whole fire door. And it's same with facades. So that's my first point. The second point is talk to a fire safety engineer early and talk to them often. As I said, we can help even if you think it's a deemed to satisfy compliant design. We can probably help you find some efficiency, but we can also guide you down the right path when you're choosing materials, which you might have thought were benign, but actually a spread of flame index of 0 could be the very worst performing material and you just don't know about it.
Thanks, Blair. Cathy.
Thanks, Amanda. I think there's a long way to go on this, and agree with Blair totally. Definitely need more testing. I'm a testing Nazi. We love testing all sorts of things and making sure that we have the systems and products to be able to help engineers and architects design the buildings they want used in the right way. I just make sure people remember to, if you're looking at other products, to check if you're reading a code mark certificate, that you actually read the exact clauses that product is assessed for under that code mark, which clauses of the NCC. Is it volume 1? Is it volume 2? Is it both? Which volume of the NCC is? When's that certificate valid to? And when you're given that certificate, to go onto the JAZANTS website and make sure it's still valid and hasn't been withdrawn. There's a lot of certificates floating around. Someone might have given you a few years ago that's since been withdrawn for a number of reasons, whether the manufacturers just don't want to pay for it anymore, whether it's been pulled for another technical reason, but to always check they're valid. And that goes the same with all the test certificates and things. The amount of times I hear people say, I've got a code mark, and you go, well, that one's expired. That doesn't even cover fire at all if you read the clauses. So make sure, I know there's a lot of documentation you've got to get through, but checking those things are very important to know what your products are tested and certified to. And that means they're third-party check that they have been done. So that's a good thing. But I know there's been a lot more questions pop up that we haven't got to. So I'm happy for people to email into the info@Brickworks email if they've got specific questions they want to address or talk about later on if they think of it, coming days. I'm happy for that to be to come through to the info@Brickworks email address. So thank you very much.
Thank you. And please join me in thanking our speakers for tonight, Blair Stratton and Cathy Inglis, for doing such a great job. As always, we're looking forward to feedback, how we can improve. So please, I would encourage you to complete the survey in the YouTube link in the description box. Thank you again for your time this evening, and we look forward to very much seeing you at the next Engineers Australia Thought Leaders webinar. Thank you and good evening.
Yes, thank you, Blair.
That's okay. It's all good. Hopefully that was informative. I learned something from listening to myself again. So,
so did I.
Yeah.
And then I realised. I realised that if I've got to listen to what you say before as well, because it makes a difference. Like,
a couple of things I would have phrased differently, specific, because you're the combination of testing. And obviously I was describing it very specifically, but what you said, that's only a part of it. It's how it all,